Hello, calculus scholars. Welcome to our first day of review. In these notes, we'll review limits, continuity, and the intermediate value theorem so that when you come to class, you're ready to jump into practice problems and more challenging practice problems. So first, let's just review what a limit is. This may seem basic, but we had some students miss this on the practice test. So let's review that the limit is the value that you approach graphically from the left or from the right. So here, if we are approaching positive 1 from the left, which is what this notation means, you're looking at the y value that you're getting closer and closer to when x is 1. So the value that we're approaching here is 1. It doesn't matter that there's an open hole or an open circle, that there isn't a value at x equals 1. It's just what value are you approaching. So the value we're approaching here from the left as x approaches 1 is 1. If we approached from the right, we are approaching positive 2. So the limit from the right is positive 2. And if we're looking at just the limit overall as x approaches 1, the limit has to be the same from the left and from the right. So in order for the limit to exist, the limit as you approach 1 from the left of f of x must be equal to the limit from the right of f of x as you approach 1. And in this case, we have 1 from the left. So this is sort of a question mark. Are they the same? It's 1 on the left and it's 2 on the right. It's not the same, so this limit does not exist. Okay, below we've got some practice problems that should be really quick, evaluating limits graphically. So do practice problems 1 through 6. Pause this video, do the problems, and then check the answers. Okay, so you should have answered these questions. The answers are does not exist, because as you approach negative 1 from the left and you approach it from the right, there are two different values, so it's D and E. On number 2, the limit is 0, because as we approach number 1 from the right hand side, it's going to 0. 3, the limit as x approaches negative 1 of g of x. So approach negative 1 from the left-hand side, we get 1. If we're approaching it from the right-hand side, it's also approaching the y value of 1. So this limit is 1. When we're doing the limit of g of x as x approaches positive 1, we can approach from the left. The y value is negative 1. When we approach from the right, it's also negative 1. So this limit is negative 1. For number 5, it asks us to find the limit of f plus g as x goes to negative 1 from the left. So remember, when we're adding two functions together and finding the limit, you can actually split it into two separate limits. So this would be the limit as x goes to negative 1 from the left of f of x plus the limit as x goes to negative 1 from the right of g of x. So when we write it as two separate limits, this problem becomes much easier. When we look at the limit as x approaches negative 1 from the left for f of x, we said earlier that that value is 1. Then when we're looking at g of x, the limit as x approaches negative 1 from the right is, let's approach from the right negative 1. That value is 1. So this is 1 plus 1, which makes 2. Okay, let's clear this so we've got room for the final one. So here in number 6, you're also going to split up the limit. So it'll become 2 times the limit as x goes to 0 of f of x minus 3 times the limit as x goes to 0 of g of x. Looking at our graphs, the limit as x approaches 0 of f of x, let's pull this down. From the right, it's approaching 2, and from the left, it's approaching 2. So this would be 2 times 2 minus 3, and then the limit of g of x as x approaches 0 approaches 0. So this is 3 times 0, so the overall value of this limit is going to be 4. Okay, so that's a review of graphical limits. There's some more practice problems here that you can do. I'm going to give the answer but not talk through a lot of the details. So here are the answers to these problems. Take a look, see if you got them right. The one thing I do want to point out or draw attention to is number 10. If you are composing two functions with a limit, the way you break that up is the limit goes inside the outside function. So it's not the limit of g and the limit of f. The limit moves inside the composition. So it's g of the limit of f as x goes to 2 from the right hand side. And we know that this inside limit here is -1. So then this becomes g of -1. And when we look at this graph, g of -1 is 2. Okay, so that is graphical limits. Next we're going to move on to tables. So again, you should pause this video, try to solve the problems below, and then check your work. Okay, so given this table, we are asked what is the limit as x approaches 2 of f of x. Approaching 2 from the left, it looks like our numbers are going down to 5. Now let's approach from the right. Our numbers are going up to 5, so the limit here is 5. In the next question, it says, what's the best approximation for the limit as x approaches 2, so it's starting the same way, of 3x raised to the f of x. The way you would evaluate this is think of 3x, and then the limit of f of x is your exponent as x approaches 2. So this is going to be 3, and x, you're going to do direct substitution, plug in 2, and then our exponent is this limit, which was 5. So 2 to the 5th is 32, times 3 is 96. So that would be your limit. Okay. Looking at the next table, it's asking what is the limit as x approaches 1 for f of x. So we can see that these x values are approaching 1. From the left, the f of x values are constant at 4, so these are headed to 4. From the right, the numbers are getting closer and closer to 1. Since they're approaching different numbers, the limit here does not exist. Okay, the third and final table, its limit of f of x as x approaches 3. So we can see in our table that we're approaching 3 from the left and the right. As you approach from the left, the numbers are getting closer and closer to 6. As we approach from the left, or from the right, they're getting closer and closer to 6 as well. So they're approaching the same number from the left and the right, but at x equals 3, f of x equals 10. Does it matter that f of x equals a different number at x equals 3? The answer is no, it doesn't matter. All that matters is what you are approaching from the left and the right. So the limit here is 6. Okay, next up, we are going to take a look at how to solve limits algebraically. Normally we solve algebraic limits using direct substitution. This is misspelled, should be substitution. If direct substitution doesn't work and you get one of these outcomes, here's what you're going to do. So if you get a over 0, that number is undefined and the limit does not exist. If you get 0 over a, that number does exist and it's 0. So 0 divided by 10 is equal to 0. Like substitute any number for a. This simplifies to 0. However, if you get 0 over 0, we say that's an indeterminate form. And then you either have to use an algebraic method to change it so it's no longer 0 over 0, or you use L'Hopital's rule. And we'll take a look at both. So in this first example, if we were to do direct substitution, we would get 0 over 0. We would have an indeterminate form. Because it's 0 over 0, we want to choose a different method. We want to get rid of what's causing us to have zeros. So we're going to factor. And if we factored this, it would be, whoops, don't forget to write the limit first. It's the limit as x approaches negative 3, and then the factorization is x minus 4 times x plus 3 over x plus 3. Well, these factors cancel, leaving us with the limit as x approaches negative 3 of x minus 4. We can now direct substitute, and once we direct substitute, you're going to drop your limit notation, and you get negative 3 minus 4, which is negative 7. Okay, in the next one, we've got some radicals. I'm going to clear the screen so I've got some more room to work for this one, because this can take up a lot of space. So if we plugged in 3 to this expression, we would also end up with 0 over 0, which is indeterminate. So we need to use a different method. And we are going to multiply, so I'm going to get rid of this equal sign, multiply by the complex conjugate. So we're going to multiply by the square root of x plus 1 plus 2, and multiply that to the numerator and the denominator. When we multiply that out, we still have the limit as x approaches 3. In the numerator, actually I'm going to write down here because I'll have more space. In the numerator, you get the square root of x plus 1 squared plus 2 times the square root of x plus 1 minus 2 times the square root of x plus 1 minus 4. Now our square roots are going to cancel. That's always going to happen. That's the point of multiplying by a conjugate. And then here the square root and the square cancel. In the denominator, I forgot to write that out, you'll have x minus 3 times the square root of x plus 1 plus 2. Okay, so this is going to simplify to the limit as x approaches 3. In the numerator, you're going to have x plus 1 minus 4. That's all that's left, this x plus 1 and the minus 4 at the end. All over x minus 3 times square root of x plus 1 plus 2. Okay, this numerator is now going to simplify to x minus 3. So now we have factors that cancel. So this is going to simplify to the limit as x approaches 3 of 1 over the square root of x plus 1 plus 2. So now we're ready for some direct substitution, which means our limit notation is going to disappear, and we're just going to have 1 over the square root of 3 plus 1 plus 2. It's going to be 1 over the square root of 4 plus 2, which is 1 over 4. Okay, so that's how we do that one. Number 3 we're actually going to skip for the moment and come back to in class. Let's move on to number 4. Number 4, you could solve algebraically, but the most efficient way is to actually think about this one graphically. This parent function is this, and the graph looks like this, with your lines at 1 and negative 1. Looking at the function we've got here, it's x minus 2. That means it's been moved to the right 2, if you remember your transformations. So our new graph looks like this. So as we approach 2 from the left, your limit is negative 1. As you approach from the right, your limit is positive 1. That means the limit here does not exist. So just think about that graphically instead of algebraically, and you'll get it finished a lot faster. Okay, let's take a look at number 5. The limit of f of x as x approaches 3. So here we're given f of x as a piecewise function. In order to find out the limit for a piecewise function, you want to look at the limit from the left and the right of f of x. The limit overall will exist if these two things are equal. So let's look at it from the left. The limit from the left, based on this function, when x is not equal to 3, it is this expression, x squared minus 9 over x minus 3. If we plug 3 into that directly to approximate this limit, we're going to get 0 over 0. You're going to need to factor. This factors to x plus 3, x minus 3 over x minus 3. So these will cancel. So that means that this limit is really equivalent to x plus 3. So plug in negative 3. Negative 3 plus 3 equals 0. So that's the limit from the left. Now that also is going to be the limit from the right, because this is the expression that's used for everything except x equals 3. So to the right of 3 it's used, and to the left of 3 it's used. So I could just change this sign to a plus, and we've done the algebraic work. So both from the left and the right it's equal to 0, so the limit overall is 0. One final example with one-sided limits. If we're looking for the limit as x approaches 1 from the right, and we're given g of x here, this says this piece is applicable when x is less than or equal to 1. So if we were to draw a number line, and this is 1, actually let me represent that differently. Think about it this way. If x equals 1 is here, to the left we're using x squared minus 1. To the right, we're using e to the x over sine of x. So we're looking for the limit as x approaches 1 from the right, so use e to the x. So this limit is equal to e to the 1 over sine of 1, and that would be the value of your limit. Okay, a couple limits that you should just memorize, or memorize their graphs. We actually talked about this one earlier. It's that parent function that looks like this. The limit does not exist. For the limit as x approaches 0 of 1 over x squared, this was one of the parent functions we memorized. These are coming together at x equals 1, but they're headed towards infinity. So we can either say that this does not exist or that it's equal to infinity. The limit of sine of 1 over x as x approaches 0 also does not exist because it's an oscillating function, so it never approaches a single value. One other one to memorize, and this is actually a limit as x goes to infinity. If we look at this graph, this one is also oscillating, but the waves are getting smaller and smaller and smaller, and so this limit is approaching 0. So those are just good limits to memorize. Okay, we said the other option to deal with an indeterminate form, 0 over 0, is to use L'Hopital's rule. L'Hopital's rule applies when you do direct substitution and you get 0 divided by 0, or when you get infinity divided by infinity, or negative infinity divided by positive infinity, any variation on that. In order to use L'Hopital's rule in a free response question, you would actually have to show that the limit of f of x equals 0 or infinity, and the limit of g of x is 0 or infinity. Then you can use the shortcut of taking the derivative of each. So here, I would need to state that the limit as x goes to 0 of sine of 2x equals 0. If I direct substitute in 0, I get sine of 0, which is 0. Then you would need, and this is only for free response, showing all this work, to show that the limit of x as x approaches 0 is 0. Since you've shown that both of those are 0, you can now use L'Hopital's rule. And we would write that this is equal to the limit as x approaches 0, and then the numerator, we're going to put the derivative of the numerator. The derivative of sine of 2x is cosine of 2x times 2. That's chain rule. Okay, now we can take the derivative of the denominator. The derivative of x is 1. So that's what our limit is equal to, and we can now plug in 0. So this is 2 times cosine of 2 times 0 over 1. this is just simplifies to 0. What's cosine of 0? It's 1. So this is 2 times 1 divided by 1, which is 2. Okay, well, let's take a look at another example. Number 2, this is also going to be L'Hopital's rule being applied, but let's show why. So the limit of e to the x minus parentheses 1 minus x, when we plug 0 in, we get e to the 0 minus 0 minus 1 minus the quantity 1 minus 0. So e to the 0 simplifies to 1, then distribute the negative, so minus 1 plus 0, this is going to equal 0. Okay, now let's show that the denominator equals 0 as well. This would be the limit, again, as x approaches 0 of x, that's just 0. So since we get 0 over 0, we can use L'Hopital's rule. So we can take the derivative of e to the x is e to the x, and if we distribute this negative, this is minus 1 plus x. The derivative of 1 is 0, the derivative of x is 1, and then we can take the derivative of the denominator, the derivative of x is 1. Plug in 0, e to the 0 plus 1 equals 1 plus 1, which is 2. So when you direct substitute in 0, originally you get an indeterminate form, 0 over 0, and then you can take the derivative of f and g and find the limit that way. You can also apply the same logic to a graph. This is a typo. That should be an integral symbol. I'm not sure why it didn't turn out correctly. So using the graph below and the fact that g, this graph, is equal to the integral from 0 to x of f of t, we are going to determine this limit. So, I misspoke. I think I said this graph was g. This is actually our graph of f of t. Okay, so let's see what the limit of g of x is. So let's think about as x approaches 0, of g of x. G of x is this integral from 0 to x, of f of t. Well, if we substitute in 0, it's the integral from 0 to 0 of f of t. We're not going anywhere, so this is just 0. Looking at the denominator, it's also going to be 0. So this is going to be an indeterminate form, 0 over 0. So we can take the derivative of the numerator and the denominator. The derivative of the numerator is going to be g prime of x. The derivative of the denominator is 1. So what's g prime of x? Well, this is the fundamental theorem of calculus. If you have the integral from 0 to x of f of t, the derivative, so this is g, the derivative is going to be f of x times the derivative of whatever this is. So this is just times 1 here. So instead of g prime of x, we can plug in f of x over 1. Okay, so let's look at this graph, and see what is the limit of f of x as x approaches 0. Well, looking at this graph, as we approach 0, it's approaching 5 pi. So that is the limit of g of x over x. We used L'Hopital's rule and got 5 pi. Okay, let's clear the screen again. We're going to do a quick trig example. Earlier in the year, at the very beginning, we taught you some different ways to rearrange trig limits, but here you don't need to. Just use L'Hopital's rule instead. So if we plugged in 0, we would get 0 over 0 in indeterminate form. So let's rewrite this as 3 minus 3 cosine of x over x. Since we're going to use L'Hopital's rule, we take the limit of the derivatives. So this is 1 minus 3 times the derivative of cosine. The derivative of cosine is negative sine of x. And the derivative of x is 1. So this becomes the limit, as x goes to 0, of 1 plus 3 times sine of x. When we plug in 0 there, we get 1 plus 3 times sine of 0, and sine of 0 is 1. So the answer here is 4. The limit is 4. L'Hopital's rule made that pretty quick and efficient. Okay, so that is the first video. We're going to have another video that goes through the second half of the notes.